All right, how's stuff? How's the homework look? All right, let's talk about bunnies. Anybody here ever have a pet rabbit?
Yeah.
Rabbits are interesting pets. You have a rat? That's cool. Rats are great. I had a friend who taught his rat how to open CDs. Back when they came with that really annoying plastic wrap that was like impossible to get into. Somehow he probably figured out that like the rat like enjoyed chewing on that, but it would chew on it. It wouldn't damage the case itself. It would just chew off the vinyl. Yeah, rabbits are interesting. They eat, at least my rabbit ate everything. Well, tried everything. I came home and the remote control, every button had one bite out of it. I had to like sample, you know, each one. So rabbit populations. So rabbits breed quickly. And let's study an idealized rabbit population. So these are special rabbits. These rabbits live forever. So they're immortal rabbits, which is bad for remote controls. And when you have a pair of rabbits and they are 2 months old, they will mate. And the next month you'll have a new pair of rabbits, which is their offspring. Okay? And we're going to look at the population of rabbits over time. So at 2 months you get a new pair of rabbits. They live forever. There's no predators. And so I'm going to look at pairs of rabbits. So I'm going to write down one. It means one pair. Or these can be tribbles that just reproduce by themselves. So at time 1, we have one rabbit pair. At month 2, let me draw a time going across horizontally. So we start off with one rabbit. After a month, that rabbit is now 2 months old, or that pair of rabbits, which means that it'll reproduce. So in month 3, that original pair of rabbits is now a month old, but we have a new rabbit pair. They have 2 offspring. And the next month, everybody ages by a month. So this rabbit is 4 months old. These rabbits are 2 months old. And since this rabbit was already 3 months old, they mate again and they have another offspring. So now we've got a new born rabbit pair. And a month later, everybody ages by a month. Well, now this pair is over 2 months, so they're going to have a new rabbit. And this pair is 5 months old, so they're going to have a new offspring. So we're going to have 2 newborn rabbits here. And the next month, everybody ages. And now we've got 1, 2, 3 rabbits that are old enough to reproduce, so we're going to have 3 newborns. And the next month, everybody ages again. And so these 2 rabbits are old enough to have rabbits along with this and this and this, so that's a total of 5 new rabbits that'll be born, and so on. And so we can calculate the total rabbit population at each point. And we started off with 1, and then 1, and then 2, and then 3, and then 2, 3, 4, 5, 5, 6, 7, 8, 10, 11, 12, 13, and so on. And this is our Fibonacci series. And I think this was the problem that led to the discovery of Fibonacci series. And it's not really all that surprising that this is happening, because in the next generation, every pair of rabbits gets a month older. And we potentially have some newborns. So how many newborns do we have? Basically, all of the rabbits from here, all the rabbits that weren't just born in this last generation, will be at least 2 months old and they'll reproduce. So in the next generation, we have the original population plus another count of whatever the prior generation was. So if this is generation N that we're looking at down here, the total population is going to be the population at the previous step plus the population at the step before that. So the population at step N is the sum of the two previous populations. And that's your Fibonacci relation.
So the number 5 is previous generation?
Which, say again?
Number 5.
This?
Yeah.
So this is so 5 rabbits were just born, right? So they're going to be part of the next population, but they're not going to reproduce yet. But all the rabbits from 2 generations ago, starting with 3 newborns and 2 that were 2 months old, all of them are going to reproduce now. So that population is going to get added to the current population, right? And that's going to give us the next population. So this is a recurrence relation. It's probably the most famous one, Fibonacci series. But recurrence relations come up in all kinds of situations. So for example, bacteria growth. So suppose initial population is 100, and suppose the population doubles every hour. So let P of n be the population after n hours. And without being terribly clever, we can write an equation for what P of n looks like, which is simply P of n equals 100 if n equals 0, because that's the initial population. But we also know P of n is twice P of n minus 1 if n is bigger than or equal to 1, because we're told every hour the population doubles. And this is a complete description of P of n. Now, it's not a closed form where we can just plug in n and turn the crank and out pops P of n. But nonetheless, it describes exactly what P of n is for any value of n bigger than or equal to 0. So it's a recurrence relation. Recurrence relation is basically when we describe a function in terms of other values of the function at smaller arguments. But we can be a little more clever and note that P of n equals twice P of n minus 1, and P of n minus 1 equals twice P of n minus 2, therefore P of n equals 2 squared P of n minus 2. And if we do that again, this will also be 2 cubed P of n minus 3, or 2 to the 4th P of n minus 4. And if we do this carefully, we'll see that this is also equal to 2 to the n P of n minus n, which is 2 to the n P of 0. And we can't say P of 0 is twice P of minus 1, but we know what P of 0 is. P of 0 is 100. So this is equal to 2 to the n times 100. And there's an actual formula for P of n. So this is sometimes called a solution for the recurrence relation. And it's a closed form representation. So we saw this with towers of Hanoi. We were moving disks around on pegs. So let Sn be the number of steps to move n disks. Well, if you only have one disk to move, S of 1, it's just equal to 1. But in general, to move n disks, we have to first move the top n minus 1 disks to our spur post, and then we have to move the largest disk to the destination post, and then we have to move those n minus 1 disks from the spur post to the destination post. So it's 2s n minus 1 plus 1. This is for n bigger than or equal to 1. And so that's another recurrence relation. We can describe S in terms of earlier values of S. And all these recurrence relations really easy to code up, right? Just like we did with Fibonacci. We could write a function for P of n that says if n is 0, return 100, otherwise return 2 times P of n minus 1. And lots of things can be written like recurrence relations, so factorials. Factorial n is 1 if n is equal to 1. It's n times factorial n minus 1 if n is bigger than or equal to 2. All right, ready for a weird one? This will be your Friday. Now, this won't be the weirdest thing we've done on a Friday. This will be a bit of weird Friday weirdness. So how many n-bit strings do not contain 2 consecutive zeros? So let's look at 4-bit strings. Everyone knows how to write these, right? All right, how many of these do not contain consecutive zeros? Well, let's find the ones that contain consecutive zeros. And I think that's all of it. So we're left with 1, 2, 3, 4, 5, 6, 7, 8. So f of 4 equals 8. So f of n equals number of n-bit strings not containing consecutive zeros. So f of 4 equals 8. What's f of 3? Is that a question or an answer? 6. You only got like 9 possible guesses. So let's start naming some 3-bit strings that don't contain 0, 0. 1, 1, 1.
1, 0,
1, 0, 1.
1, 1, 0.
What one?
1, 1, 0.
1, 1, 0. 0, 1, 1. 0, 1, 0. Any others? Are we good? Should we run with this? I think I'm good with that. All right, let's do some 2-bit strings that don't contain 0, 0.
0, 1, 1, 0.
That's pretty much it, right? How about 1-bit strings that don't contain 0, 0?
1, 2.
All right, either 0 or 1. How about 0-bit strings that don't contain 1 or 0? Well, that's a bit of an existential question. But
0.
yeah, or maybe 1.
It depends.
Depends, so we won't go there. We got 2, 3, 5, and 8. Does that look familiar? It's looking a little Fibonacci-ish. But it's only 4 numbers, so it's hard to find a pattern.
If we knew f of 5, maybe.
If we knew f of 5, anybody want to do f of 5?
No thanks.
No thanks. Well, we did f of 4. What if we wanted to have 5-bit numbers? We could have this repeated down here, right? This would have 0s in the beginning, and then we'd rewrite this, but we put 1s in the beginning. That's the way I teach in 120 to do these truth tables. So all of this with 0s in the beginning, and then the same thing with 1s in the beginning. All right, suppose we put 0s, we'll do purple 0s. Suppose we put 0s in the beginning of these. Well, anything that already had consecutive 0s in it is still going to have consecutive 0s. So that's not going to change. But what are we going to have to throw out by putting 0s in the beginning here?
Any of them that start with 0.
Any of them that start with 0. So all of these are now out of contention. But anything that started with a 1, by putting a 0 in front, we're not going to add a consecutive 0, 0 anywhere. So how many things are we going to have from our list like this? 1, 2, 3, 4, 5.
And then plus whatever all that is, what we had before, so it'd be 5 plus 8, because 1s wouldn't change.
Yeah. So this is a bunch of things that start with a 1 in the beginning, which means whatever we throw out from here is a 3-bit string with consecutive 0s. So the number of things we have in this list is f of 3. That's our 1, 2, 3, 4, 5. And then as you just said, if we put 1s in the beginning instead, we're not going to change any case of having consecutive 0s or not having consecutive 0s, because we're putting a 1 in the front. Whether there's a 0 or a 1 here, it doesn't change the fact that there is or isn't. So the number of things we're going to have in here is going to be f of 4. And so f of 5 will be f of 3 plus f of 4. And there was nothing magic about starting with 4. We could do this for any number of bits. So for f of n, if you want to get to f of n plus 1, you just break it into 2 cases. If we take all of those numbers with n bits and we put a 0 in the front, we lose half of them. And we preserve however many n minus 1 bit strings didn't have consecutive 0s. And if we put 1s in the front, then all of those that didn't have consecutive 0s before still don't have consecutive 0s, so that's f of n. So we get this general relationship, f of n plus 1 equals f of n plus f of n minus 1, and that's the Fibonacci relation. So that's a famous recurrence relation. And let me give you one weird thing. And we can prove this, but we're not going to. But there is a way to solve this recurrence relation and come up with an expression for the nth Fibonacci number. And it's a little bit weird. But that formula gives you the nth Fibonacci number. And it's not even clear that that has any business being an integer, but it is. And you can pop that in on your calculator, set n equal to 10 or something, and you should get a nice integer. It should be the 10th Fibonacci number.
So n only integer.
And only an integer, yeah. I don't know what it means if it's not an integer. I guess you could have fractional Fibonacci numbers.
You can try it, see what comes out.
Yeah, or you could try it. All right, so questions about whatever the heck we've been doing. What have we been doing? Counting, primarily. Pigeonhole, combinations, permutations, and recurrence relations.
So if m equal 1, so f m gonna be 1.
Okay, cool. Let me know if you get a fractional one. Maybe we should graph it. All right, ready to change gears?
Yeah. I'm getting to it.
Okay.
I got enough for it.
So we got 2 weeks left after today. So we're on schedule. What I want to talk about for the next few classes is some graph theory. Normally I would talk about trees, but most people here are also in CSE 222, and we've been doing trees for weeks. And if you're not in 222, you'll be in 222 at some point, presumably. But graphs are kind of a generalization of trees. So we'll get some discussion of trees by talking about graphs. But trees have very particular properties. For example, there's a node called a root, and the root has no parent, but all other nodes have parents. And we have no cycles. You can't come from a node and have a child who's actually a parent or a grandparent. So they're very particular types of things. But we can generalize what we do with trees and create what's called a graph. So let me show you some pictures of graphs first.
It won't let me graph it.
Oh, really?
Yeah, but when I type in 1.1, it's undefined. 1.2 is 0.54, 5, 6, 7, 7. 1.3 is undefined. 1.4 is 1.10.
That's weird because
is undefined.
It should be defined because you can raise. Oh, 1 minus square root 5. Oh, this might go negative. That should be okay. You got me curious now. Alright, I'll have to play with it later too. So there's something to do on the weekend if you're bored. Hop into MATLAB or Scilab or something and
Desmos is graphing that as a straight line. It takes
Probably shouldn't be straight because the Fibonacci's accelerate.
Then
But I'm guessing it should be smooth.
if n equal 5 and n must be 5 too.
5 is 5.
Yeah.
For me, divergence graphing is a series of points. No, it's on everything. It's odd.
All right. We'll see what that does over the weekend. I'll take a break from grading PA5 and do some fractional Fibonacci's. So here's an example of a graph. I've got 5 circles and they're connected with lines. That's basically what a graph is. A bunch of circles with a bunch of lines connecting them. That's the non-mathematical description. But that's basically what we're going to be talking about. Okay, this is a really simple graph. It's got 3 circles and 3 lines. This whole thing is a graph. It's got 5 circles and 4 lines. But it looks kind of different from this graph because there's circles up here I can't get to from these circles. So this thing on the left we call a connected graph. Everything is connected to everything else. This is a disconnected graph, but still technically it's a graph. But we're not very interested in disconnected graphs. Here's another example of a graph. It's just 4 circles with no lines anywhere in sight. But that's another disconnected graph, so we're not very interested in that either. It's possible that my graphs, some of these lines might have directions associated with them. In which case, you know, some of them might have 2 lines, one going in each direction. So this is a directed graph, and we will be interested in directed graphs. But even without direction arrows, we could have a graph that, for whatever reason, has multiple lines between the same circles, and that's still a perfectly valid graph. But it's not as simple as, say, this. We can have a line between a circle and itself, and that's completely legal. So there's 2 circles and 3 lines. So these circles are called vertices, and the lines are called edges. And one thing we want to be really clear on up front is that the way we draw a graph is not really important. So let me show you a few graphs that are considered the same. So there's one graph. Here's another graph. These are considered to be exactly the same. They look different because I've placed them differently on the page. Here's another. And that's exactly the same as those other 2. And the way I can tell they're the same is because if I make these edges out of rubber bands and I make these vertices things that I can move around, I can move this around and turn it into that shape or that shape. As long as I don't break the rubber bands, I end up with something that's basically equivalent. So the fancy term is isomorphic. Isosame morphic shapes are having the same shape.
Apparently there's a fraction that generates all the Fibonacci numbers in order, every 24 digits.
Really? Cool.
It's all zeros and in like stacks of 24, and it's all zeros and the last like bit of 24 is the Fibonacci.
Huh. Cool.
It's 1 over 999 for a little while.
Really? That's freaky.
Yeah. It just generates them all in flashes of 24 where everything is 0 except for the last one.
That's really freaky. Cool. Fibonacci numbers are pretty impressive. Alright, so graphs, we don't really care how they're laid out on paper. They can move around, they can stretch, and they can shrink. But what is it that we're interested in? We're basically interested in which vertices are connected to each other through edges. That's really the important part. So here's a graph. And here's a totally different looking graph. But do you think these are isomorphic? Yeah. If I were to take these two and just kind of like flip them over, right, this would look exactly like that.
Or if you kind of think in like 3D space, you just lift it.
Yeah, yeah. All right, so let's look at this stuff more formally, but that's the basic ideas we're going to be interested in. So a graph is an ordered pair of sets V and E. So V is a set of vertices, E is a set of edges. And V cannot be the empty set. You got to have at least one vertex. But you don't necessarily need any edges. Each edge has one or two endpoints. And an endpoint is a vertex, so has one or two endpoints which are elements from the set V. And we can say the edge, an edge connects its endpoints. So in these examples, right, this is an edge and it connects this endpoint to that endpoint, two vertices connected to each other. And what can we represent with graphs? All kinds of things. So this could be a system of roadways where these are particular locations and the arrows show you the one-way streets that you can use to get from one point to another. Right? And here we might have a two-way street between these 2 points, so you can go that way, you can go this way. But from here to here, there's only a one-way street. And there's probably some place we can't reach if we're not careful. You could represent computer networks with graphs. So they're usually not directed, but we might have, you know, a series of systems. And maybe it looks like this. And maybe this is some kind of server, and this is another server, and maybe these are customers, and maybe this is the network that is used to send internet traffic around campus. And so here we are over here in the STEM building. So we can make acquaintance graphs. And so our vertices here are people, and an edge means that these two people know each other. They're connected on Facebook or something. And so A and B are connected, and B and C are connected, and so A and C are indirectly connected. And we can say, what's the strength of that connection? Well, they're connected through one intermediate contact, whereas A and F are connected through two intermediate contacts. And A and G are connected through 1, 2, 3 intermediate contacts, but A also has a direct connection to G. And so as people add to the system and they create new contacts with friends, this graph gets updated. And you get these recommendations like, you know person C. Hey, do you know person B? Maybe you'd like to make a contact with them, so it sends you B's information. And maybe you can get a link like this.
Wasn't there some sort of study or something where you can be connected to someone else in the world through 6 people or something like that?
Yes. So, the Oracle of Bacon. So, name a favorite actor or actress.
Tom Hardy.
Tom Hardy? So this finds movies that people shared with each other that get you from Tom Hardy to Kevin Bacon. So Tom Hardy has a Bacon number of 2. And it's really hard to find people with large Bacon numbers. So William Shatner, Bacon number of 2. And we did this one year. Donald Trump, Bacon number of 2.
What about Donald Glover?
About Tom Cruise.
Oh, that's gonna be easy. Glover.
Glover, not Gulliver. Donald Glover, Bacon number of 2.
Can we get anyone higher than 2?
It's not easy. Tom Cruise, Bacon number of 1. So this is fairly remarkable, right?
Sylvester Stallone.
There we go.
Oh, yeah. What about Jackie Chan?
Jackie Chan's everywhere. Sylvester Stallone, Bacon number of 2. Kung Fu Panda, there you go. So what's up with this? Well, obviously there's nothing special about Kevin Bacon here, right? It's a kind of arbitrary choice. Certainly anybody who has a Bacon number of 2 and somebody else who has a Bacon number of 2, their number relative to each other is no bigger than 4 because they're connected through Kevin Bacon, right? But in fact, you could do this with just about anybody and get similar results. And this is just a big acquaintanceship graph, right? So you go through and you build a database of movies and you find all the actors and actresses and you just add links for everybody who's in the same movie. And then if you want to find a Bacon number, if this is Kevin Bacon down here, and you want to find E's Bacon number, you're looking for the shortest path from E to G. And we'll talk about some shortest path algorithms later. Sorry?
Which would be EAG.
Which would be EAG as opposed to ECFG. Exactly.
And I did find a graph for the Fibonacci thing. It's
Okay.
The issue comes up where if it's not a whole number,
Mm-hmm.
it gives you imaginary numbers.
Oh, okay.
But you can get a graph that kind of it takes off the imaginary part,
Okay.
and it
Does it look smooth?
is smooth
Okay.
until like you get into the negatives.
Oh, cool.
Yeah, it's
Can I throw that up on?
yeah.
This is the Fibonacci.
There we go. Fibonacci numbers, yeah.
Fibonacci
So that part's
numbers.
kind of what we expect. But then we got like interesting stuff on the negatives.
And then if you added in the imaginary stuff, it would kind of be a red line on the bottom.
Okay. Wonder what happens if you take magnitude of the imaginaries. That's cool. All right. All right, more terminology. So a directed graph So basically each edge has an arrow, a direction associated with it. And so an edge is given by an ordered pair of vertices where this might be U and this might be V. So U is the initial vertex and V is the terminal vertex. It starts at U, ends at V.
Is SE graph?
Each edge is given by U comma V. Yeah. Okay, so one thing we want to do is we want to be able to represent graphs inside a computer. We want to be able to take these pictures and somehow store them in a way that makes this and this and this all basically be treated the same, or that and that treated the same. So we don't want to just store some kind of picture of how this was drawn on paper, but we want to capture the essence, which is basically what's connected to what through which edges. And we've got a few ways of doing this. So a few more definitions. So two vertices, U and V, are adjacent if they're connected by an edge. So two vertices are adjacent if there's an edge connecting them to each other. And edge E is incident to a vertex U if E connects let me say it. An edge E is incident to vertices U and V if E connects U and V.
So you could say E is incident to U, or it is incident to
Yes,
V,
it's
or
incident to both. Yeah. So let's just do some pictures. Okay, so A and B are adjacent, B and C are adjacent, B and D are adjacent. And let's call this edge E1, E2, E3. So E1 is incident to A, E1 is incident to B. E3 is incident to B and C, E2 is incident to B and D.
So B will be the root.
No, there's no root in the graph, because we could also have you know, a vertex E that looks like that. So if we want to represent a graph, we've got a few ways to do this. So the most straightforward way is probably an adjacency matrix. So what do we do in an adjacency matrix? Two-dimensional matrix. And we basically list all of the vertices. So vertex 1, 2, 3, 4, down to n. And list the vertices across horizontally. And if two vertices are connected to each other, we put a 1 in that corresponding position. Otherwise, we put a 0. So really straightforward binary matrix. And wherever there's a 1, it means two vertices are connected to each other. And if we have a case where there might be multiple connections, we could have, you know, a 2 to say there's two edges connecting those two vertices. So we can handle that case. Another thing we can do is sometimes when we have a graph, we have what are called weights associated with each edge. And a weight might be like a distance. If you were making a map, and these were cities, and these were roads from one city to another, it might be useful to record the traveling distance along each of these roadways. And so we might make a weighted graph. And this says the distance from city A to city B is 45, and so on and so forth. And we can store that information inside an adjacency matrix also. And there's other ways that we can store matrices, and we'll talk about those in a little bit, but adjacency matrix is sort of the first one that comes to mind for most people, because it's really just capturing the essence of the graph, which is here's all my vertices, tell me about the connections between them. All right, let's do a quick 5-minute break, and then we'll go over some theorems related to some of these properties.